This is problem number 70 in chapter 5 of the Giancoli textbook. It reads, at what distance from the Earth will a spacecraft traveling directly from the Earth to the Moon experience zero net force because the Earth and the Moon pull with equal and opposite forces? So we should recognize, obviously, that the gravitational force from the Earth is much larger than that of the Moon because of its size, its mass more specifically. Let's go ahead and make a quick sketch, recognizing that the distance from the Earth and the Moon we can call distance d. And if this little dot here is the spacecraft, then we should also recognize that there are some other interesting notable distances that if we were to call this distance, let's take a look at the distance from the center of the Earth to the spacecraft. If we were to call that distance x, then the distance from the spacecraft to the Moon would be d minus x based on the sketch that we've made here. We should recognize that f sub g on the spacecraft, between the spacecraft and the Earth at that point must be equal to the gravitational force between the spacecraft and the Moon at that point. That basically allows me to write two equations and set them equal to each other. I can now say that g times the mass of the spacecraft times the mass of the Earth divided by x squared is equal to g times the mass of the spacecraft times the mass of the Moon divided by d minus x squared. Now that I've established that, I can kind of eliminate some of these terms. The gravitational constant g, big G, goes away. The mass of the spacecraft also goes away, and I can rewrite this expression as mass of the Earth over x squared is equal to mass of the Moon over d minus x squared. If I take the square root of both sides, it'll allow me to isolate the variable that I'm looking for, which is x, a little bit more quickly. So I'll take the square root of both sides, and when I do that, I get mass of the Earth, or root mass of the Earth divided by x is equal to root mass of the Moon divided by d minus x. Okay, at this point what I'm going to do is I'm going to cross multiply. So let me pan down here, and actually what I'll do is I'll kind of start working up here in the left hand corner. So now what I get when I cross multiply is I get x times the root of mass of the Moon, and I'm going to set that equal to d minus x times the mass of the Earth. And again, continuing to, I'll go ahead and distribute these terms over here. I get x times root mass of the Moon is equal to d times root mass of the Earth minus x times root mass of the Earth. I'm going to combine these like terms here. I'm going to add that to both sides, and I'm going to get x times root mass of the Moon plus x root mass of the Earth is equal to d times the root mass of the Earth. I can factor out the x here since that's the variable I'm trying to isolate, and I get x times the root of mass of the Moon plus root mass of the Earth is equal to d times the square root of the mass of the Earth. Okay, again, I'm trying to isolate this variable x, so I'll continue to work on that. I'll divide both sides by this term here, which is basically the sum of the square root of the mass of the Moon and the mass of the Earth. I'll divide both sides by that term, and so finally I get x is equal to this distance d times root mass of the Earth, and I'm going to divide that whole thing by the sum of the roots, mass of the Moon and the root of mass of the Earth. And now I can plug these things in. I know the distance d. If I go back to the kind of top of the page here, we can see that d is the distance from the Earth to the Moon. So and that's known. And let me go ahead and plug these numbers in. I'm going to get something on the order of 3.84 times 10 to the 8th meters. And I'm going to multiply the square root of the mass of the Earth. Again, that's known. 5.97 times 10 to the 24th kilograms. And I'm going to divide that by these interesting numbers here, the square root of 7.35 times 10 to the 22nd kilograms. That's the mass of the Moon. And I'm going to add to that again this value for the mass of the Earth that I've seen here in the numerator, 5.97 times 10 to the 24th kilograms. Running that all through my calculator, and I finally get this value for x, and that's going to be equal to 3.46 times 10 to the 8th. 3.46 times 10 to the 8th meters. And that is approximately equal to about 22 moon radii. So that is the solution to problem number 70 here in the green box from Giancoli Chapter 5.